All right. Last 5 minutes, I want to tell you about a heated controversy. Yes. So I want to calculate the amount of potential energy that's stored, the gravitational potential energy that was released when the Earth formed. Because in the controversy, this was used by Lord Kelvin to estimate how old the Earth could possibly be, figuring that if it started at a molten state and it cooled down and solidified, that this source of energy, the gravitational energy that was released, would be dissipated in a time that was on a scale of 100 million years, tops, he said. Okay, so I want to calculate the gravitational potential energy released when Earth formed. So how am I going to do that? This is a problem, because as I'm building up the Earth with successive layers, the gravitational potential of the next little bit that I bring in cares about how much I already brought in, sadly, right? The formula for gravitational potential energy is minus G m over r. But r keeps changing, and so does the amount of mass that I've already brought there. So I have to use calculus. I have to set up. So, yeah, I know. You're supposed to say calculus, yay. All right. That was really good and vigorous. I appreciate your... Okay. So suppose that at some point I have already accumulated radius r. I'm going to be really cheesy and say the density of the Earth is uniform. We know it's not true now, but they didn't. So we're just going to make that as a crude approximation. Okay? So there's going to be a little bit of mass in a shell of little thickness, dr, that I bring in. And as that falls in from infinity to be assembling the Earth, it will release a certain amount of gravitational potential energy, because it started with 0 and it ended up with a negative amount. And I need to then figure out how much that is. So I have a question for it. How does the mass of what's already here depend on the radius if it's a uniform density? No. I don't want all the constants. I want to be cheap. Okay, let's say that the mass of the entire Earth is m sub e. So I want to know what's the mass at radius r. So I've already built up a smaller radius r. How does that depend on the radius? Is it little r to big R? Is that right? Cubed, right. Okay, it has to go to 1 when little r goes to big R sub e. And it depends on the volume, and the volume depends on the radius cubed. Okay, so the gravitational potential energy of this shell will be minus G m sub e r over big R cubed. I get to divide by an r. And I now need to know how much mass, little dm, that I bring in. How am I going to get dm from this picture? I want to relate it to dr. So how much mass should there be in that little infinitesimal shell of thickness dr? So we just open it up. It's like an orange peel. We lay it flat, and it will be the surface area times the thickness. So dm will be, if you like, the mass density times 4 pi r squared dr. Agreed? Open it up, lay it flat. Okay, so du is minus g m r. How many r's? 3 plus 2 minus 1, 4. Get out of the way. 4. And we have a 4 pi. We have 3 r sub e's in the bottom. And we have a dr. And a rho for good measure. Okay, so this is what we're going to integrate. What are the limits? 0 to the radius of the Earth. So we get minus big G mass of the Earth, radius of the Earth to the 5th power rho 4 pi over 5, and radius of the Earth cubed. Yuck. Okay, I want to swipe some powers of the radius of the Earth to convert rho and 4 pi and stuff into the mass of the Earth. So this is going to be minus g m sub e times 4 pi over 3 times 3 rho radius of the Earth cubed. And now, how many factors of radius of the Earth? I only had 2. I used 3, so I need to put 1 on the bottom. And the part that's in parentheses is the mass of the Earth. So I have minus g mass of the Earth squared, minus 3 over 5 times radius of the Earth. Check my dimensions. Does that work? Maybe. Yeah, for that's the form of potential energy is gmm over r. So that works. So Lord Kelvin understood this. He understood something about the properties of rock, and he made an estimate. And he said, look, if the Earth started in a molten phase and cooled down from that, it could only be 100 million years old. Who's the guy on the left? Chuck Darwin, right. And he had already said that the fossil record needed to be over 1 billion years old in order for evolution to have done its thing. And so it was a big controversy, and the physicists said the biologists, well, Darwin was nuts. But you know better. What was the reason that Kelvin screwed up? Actually, radioactivity. So he did not know about a source of energy that is being produced. And so it's not just cooling, but there's actually energy being liberated. That's part of the story. The other part is that he made too simple a model of the cooling Earth. All right, folks. See ya.